Yeah, let's delve into it. Thank you very much. Thanks for also Annika and Elke kind of making me come here, invite me. As you said, I'm Jan from Tübingen, and I'm very happy to present our work on tracking language model usage in scientific publishing. And a little bit of background, the paper title that you see on the slides is from this preprint that we published in 2024, and that just last week also got accepted to Science Advances, which makes us very happy, obviously. And the project itself was led by Dimitri, who's there on the left, and Rita, Agnes, and I did some contributions to it. And the main question we wanted to answer is this one: how many papers are really written with the help of large language models? And all of us are data scientists by training to some degree, so we really wanted to answer this question as data-driven as possible. And before I get into the results of our work, I want to quickly say a few words about how other people measured these things and why it's actually important to care about the use of language models in scientific publishing. Okay, so as you probably all know, language models can produce extremely realistic sounding output. And when I gave this talk for the first time, that was in Mainz, and it was Carnival season. So I did a little mini study with my lab where I had these two texts on the Mainz Carnival posted to our lab's teams and asked my colleagues which of them is the ChatGPT one, which of them is the real human written one. And I mean, you can look at it for a few moments. I can tell you already, people from my lab, they just couldn't tell. And in fact, the right one, the blue one, is the one from Wikipedia. And I guess all of us have kind of experienced this surprising naturalness of the output. And of course, that means with the right prompt, you can nowadays get texts from almost any genre from language models, and that of course includes application in research. So what you see on this slide is a very early poll from Nature. I think it's from summer 23. So half a year roughly after ChatGPT was available, and it asked 1,600 researchers, what are you using language models for? And they use it for a lot of things. I picked 3 examples here. Roughly a quarter of the sample says they use it for manuscript writing, another quarter said they use it for literature review, and roughly 15%, maybe a bit more shady, also use it for their peer review work, right? So that's that basically points to the fact that researchers find language models very helpful, and I think that makes sense because research is heavily relying on text, often on English text, and not all of us, actually only the minority of us, is English native speakers, so it's really something that also makes science more accessible to people who don't come from an English-speaking background. That sounds like a good thing, but you also all know that there's reasons to care about language model usage, and that is that language models, of course, make some mistakes. They can hallucinate, so 2 important examples of that are first made-up references. So this overview here from Scientific Reports 23 summarized a few studies on that, and they find that between 20 and 90% of all references, depending a bit on the use case, are or can be made up. And the second example for relevant hallucinations in science is unfaithful summarizations. And in this study, they find, depending on the model, that only 70 to 90% of the summary statements are correct. And of course, these 2 things are like severe limitations when you work with your language model to write your manuscript, because you can imagine you write your related work section and ChatGPT might just cite a paper that doesn't exist or cite a paper that does exist slightly incorrectly, and then somebody else reading a paper getting the wrong idea. And of course, that's bad. And that is even worse because language models can sound very convincing, especially when they are wrong. They can be really insisting on what they think is true. And all of this is already bad, but only considers a good faith user that wants to check their things and wants to do the right thing. But you can also imagine that there are institutions like paper mills that basically want to produce as many papers as possible in a short time to sell them, basically. And connecting that with language models, of course, means that there will be a lot of trouble. So for these reasons, because there might be scientific integrity problems with language model usage, it's really important to somehow track how much these models are used, and this is what I want to talk about. So first, how can we even detect language model usage? And what people have noted early on is that language models seem to prefer certain words. Here are a few Twitter screenshots from the time when Twitter was still a place that didn't drive you insane the moment you open it. So in these screenshots, Paul Graham noted that the word delf was somehow suspicious for language model output, and someone else replying that delf, safeguard, robust, demystify, all of that somehow sounded like ChatGPT. And like the fact that people noted that in their daily lives, I think, is already some clue that there might be these marker word traces in language model written text. People also analyze that more quantitatively. This is an analysis from March 24, where Philip Shapira from Manchester University, looked at the word delf in the OpenAlex paper database and saw that while papers with that title were basically not existing until 22, they had like I think it's a 15-fold jump after ChatGPT came out. So there's really clearly these traces that scientific writing somehow changed when language models came out. So how can we look for these changes a bit more systematically? So there were already previous to our work, that tried to use these ideas, and the first idea is basically to just look at small sets of marker words. There are a few studies like that, and they all basically do the same thing. They choose some control words, they choose some marker words, plot them over time, and from the difference here in blue you can see 23, when ChatGPT came out, some words go up. And of course that has the upside that it's very simple, and the downside that you somehow need to know what these marker words are. So that's the first idea. The second idea is to use language model detectors. That's something that we also just talked about before the talk. Basically, you train a deep learning model to detect language model written text and discern it from human written text. And then what you do is basically you apply your trained detector to papers over time. For example, apply GPT-Kit to it, and then what you will get is like detection curves over time. So these 4 different colors are 4 different detectors, and then you can see that all of them somehow, their detection rates goes up after ChatGPT is released. Of course, there are some problems also with this approach. One is, first of all, you need ground truth text. That means some researcher needs to sit down and compile a set of example abstracts or example papers written by a language model. And this will inevitably lead to a training bias, because it's impossible for a single researcher to decide how other researchers might use language models. So the language model text that you have in your training data will very likely not be fully representative of all the actually written language model assisted texts. So there's a training bias that you really can't avoid. And the second problem is that the black box model itself is not interpretable, so it will not tell you why a certain text is judged as human or language model written, at least not like out of the box. That can be a downside. And the final downside is that with this approach you can only do language model detection, but you can't really put the results into context, so you can't compare it to other interesting changes that might occur in scientific writing. Okay, that was the second idea. The third idea is a little bit similar, so it's an explicit model of language model versus human generated text. And there what you do is you again have some ground truth data from which you learn which words are more likely in human text versus in language model written text, and then you can basically extract marker words and do similar analysis as we saw before. These models basically have the same problem with the training bias, because you again need the ground truth corpus of language model and human written text. So in summary, all of these 3 methods basically have 2 problems. They require these ground truth data or previously selected marker words, and these ground truth data are usually not representative of the real world use cases or prompts that researchers really use when they use language models to write or revise their text. And the second problem is that all of these methods solely focus on language model usage, so they can't compare any language model induced changes that they track with other changes that have occurred. And our method tries to avoid these two problems. We want to track language model usage fully unsupervised, that means completely data-driven, so without any ground truth text or marker words. And we also want to track other changes. Okay, and to explain how we got the idea, I will go to a concept that might seem a little bit removed from text data, and that is the concept of excess mortality. So you probably remember excess mortality from the COVID times. What you can do with excess mortality is you can track the number of deaths that are related to some unusual, out of the normal course of deaths, and you can directly infer it from the raw mortality, and here's how it works. So this is in dark blue, the real mortality, the raw mortality from all over Europe starting in 2020. And these peaks you see are the COVID waves that we had. And in the background, in gray, you see the usual death rates over the years. And you see that there's like the seasonal peak in winter, because in winter we usually have more death cases. And then to extract the real COVID death, just from these raw numbers, you basically ask how much do these peaks exceed the seasonal trend. And by that, you basically get the COVID death for free from the raw mortality if you have this baseline period. That's very powerful, but of course there are some caveats. You only learn how many COVID deaths there were. You don't learn for an individual death, was this particular death due to COVID or was it due to something else? And if there's a confounder like a simultaneous heat wave or a simultaneous flu outbreak, you would not be able to disentangle. You must know somehow independently that COVID is going on. So you can't completely tell that just from the data. So despite these caveats, it was actually possible to use the concept to improve COVID death estimates, or at least cross-check them during the pandemic. And we now want to take this concept and apply it to real scientific publication data. Before we get there, I have to quickly introduce our dataset. And our dataset is a PubMed dataset. You might know the PubMed database. It indexes abstracts and papers from biomedical research, not only like strictly biomedicine, but also more removed fields like education and nursing, and also very technical fields from STEM like physics and informatics. And they usually contain published work, not preprints, or not so much at least. And we took all the entries from 2010 to 2024, so 15 years, and that gives us 15 million abstracts. So that's roughly 1 million abstracts in PubMed per year. And then to give you an idea of the diversity in this dataset, here's a t-SNE embedding that my colleague Rita made in an independent paper. Each dot in this plot is a single abstract embedded by its similarity, so similar abstracts are embedded close to each other, and in the colors you see different fields. But for our analysis, we didn't care so much for the fields in the beginning. We really wanted to look at the abstracts themselves and look at how single word usages changed over time. And that's what you see in this plot. You see 9 example time courses. So in each of these plots, you see the frequency of different words, how they change over the years. And all of these time courses have one commonality, and that is that they have some trend that goes in a certain direction that is then disrupted by something that seems to be an important external event. In the 2 first rows, you see examples of words that changed after 22, so after ChatGPT was released. And these words like delve, crucial, potential, significant, important, they somehow, we will look at them later in more detail. But we also see stuff that is not language model related in any way. We see words like pandemic that track the onset of COVID. We see Ebola that tracks with the Ebola outbreak in, I think, 2015. And we see the slow rise of convolutional that tracks the rise of convolutional neural networks in machine learning research. So there seems to be, like, these word usages in PubMed, they somehow seem to track with the real world in some sense. And we now want to analyze this systematically using the concept of excess mortality. And to do that, Dimitri came up with the concept of excess word usage, and I will very briefly explain it with the word crucial. So what you see here is that crucial in 2010 was used in less than 2% of the abstracts in the database, and then this percentage until 22 slowly rises to something a little bit short of 3%. And then what we did is we took the trend from the 2 years before ChatGPT came out and extrapolated it to 2024, and that gave us what we would expect in 24. We would expect 3% of all abstracts to contain crucial. But what we observe is that actually 7% contain crucial, and this difference is the excess gap that we observed. And this gap you can quantify in two ways. You can either quantify the absolute gap, that's 4% in this case, or you can compute the relative gap, which is a factor of 2.3 between these numbers 3 and 7. And why is this distinction between absolute and relative excess important? You can see this on this slide. And that is basically because rare and common words work a little bit different here. If you have a rare word like delve that was basically inexistent before ChatGPT came out, we only have an increase from basically 0 to 0.3%, so that's in absolute terms tiny, but it's almost 30 times increase in relative terms. So for rare words, the relative excess estimate works better, it's more sensitive, but for a more common word like potential that was already at 20%, we see a 5% increase, which is like, I think, the largest excess that we ever found for any word in the data, but it's in the relative terms only 1.3 relative excess. So that's why these two measures are important, and I will use them on the following slides basically in parallel, because relative is more sensitive for the rare words, and absolute is more sensitive for the common words. Okay, so we now, of course, wanted to see how is this excess for the ChatGPT. So what you see here is the excess use in 2024, so comparing the 2024 expectation against the actually observed values for 24. And you see here, each dot is a word. We looked at all words that occurred in at least 100 abstracts, so it's not all words, it's roughly 27,000. And you see the excess usage on both plots here is relatively low, but that is only because I was hiding the like roughly 100 or a few hundred most important, most accessing words basically. So for most words, these values are super low, and then there are these outliers. And I labeled these outliers here, and there are again these ChatGPT sounding words like delve, showcasing, crucial, comprehensive, and so on. We defined these thresholds that you see here basically to make a cut to say everything above that threshold is an excess word. This is a bit arbitrary, I admit, but you have to draw a line somewhere. And now we wanted to know, are these plots special? So do other years just look the same, and every year you have like a few hundred words that become suddenly much more fashionable? Or is the ChatGPT year really different? And it turns out, if you look at 2015, where we had this Ebola outbreak, there's basically no absolute excess for any word that is above the threshold we had in the ChatGPT year. And there's a few words that seem to be related to the Ebola case, so Ebola itself, Sierra Leone is there, a few other things. But these effects are much lower in magnitude. And then I have the COVID year as a second comparison, where you see there are excess words that have like the same magnitude, so similar strength of excess for coronavirus, because that was basically completely, like, coronaviruses were known, so the word was in the database before, but they were of course much more focused in these years. But it's much fewer excess words. And there's a second difference that is, if you here see on the left the COVID excess words, they are all more or less directly related to COVID from their content. So we call them content words because they are nouns or adjectives that refer to a specific topic. But the ChatGPT words are mostly style words, so underscores, delves, showcasing, offering, pivotal. You can basically say these fluffy words in any context. And if you plot this trend over the years, you see these two things very clearly. So these LLM era years, they have much more excess words. So they roughly have 2 times more excess words than the COVID years. they have roughly 10 times more accessed words than regular years, and they have like this high proportion of style instead of content accessed words. And that's really nice for us because now we have this list of style words that are not related to a specific topic and that we are very suspicious of them being like these special words that ChatGPT and so on like. And we have not obtained them by like training a model or something, but we have obtained them completely data-driven just from the raw word counts, basically. And now what we want to do is we want to use them, like these style words that you see there in orange, we want to use them for the language model tracking. To show you, before we do that, to show you that this is actually like a real interesting set of words, what we did is we searched PubMed for 3 of them. We searched them for abstracts that contain delve, intricate, and meticulous. And the abstracts that we find, without any cherry picking, look like this. So this is really the first abstract that I found, and it has sentences that is basically riddled with these words. So all the yellow ones are words from our list, and there are sentences that sound like, by meticulously delving into the intricate web, blah blah blah, comprehensive, significant explores, and so on. So, and we found this for several abstracts, and for us that was kind of strengthening the intuition that these words are really highly correlated and put into the text by a common source, and we suspect that this is large language models. So this now comes back to our question from the very beginning: how can these words now help us to put a number on that? How can they tell us how many abstracts were actually written with the help of language models? And I will again explain this with this example here. So for the word potential that we saw before, this single word has 5% absolute excess usage. So that excess gap is basically word usage that we can't explain other than saying it must have been due to language model usage. So we know that based on the single word only, we would say that there's at least 5% of abstracts written by large language models. But of course, this is the single word excess gap is a lower bound because not every abstract will use the word potential. Basically, another abstract that is generated by a language model might use other style words, and that means by combining these style words, we can basically tighten this lower bound and get closer to the true value. So what we did is we generated 2 marker word lists in slightly different ways. I will skip the details, but I can say that we have one list that has rare style words and one list that has common style words. And then for these words, we basically ask how many abstracts have any word that is on these lists. And then what you get is you get basically similar curves as before. So for this one, you see how many abstracts in each of these years had any words from the rare list or from the common list. And then you can again do the same thing as before. You can compute from the baseline trend, you can compute what you would expect for 24. You can compute the gap. And the number here, these 13% roughly for both lists, we get 13%. That basically answers our question. So based on this marker list work, we would argue, on this marker list words, we will argue that at least 13% in the PubMed abstracts were somehow processed with large language models. So that's the main result, but we also zoomed in a bit closer. So we looked at subfields, and what you see here in the scatter plot is basically, this is our estimate based on the rare words, this is our estimate based on the common words, and each dot is a field. So fields that are on the lower left have little estimated usage, fields on the top right have high estimated usage. And you see that fields like computation, healthcare, and environment are higher up than fields like ethics, rehabilitation, and ecology. We saw kind of a trend that more technical fields are higher on the right, like have higher usage, roughly 20% or 24% for computation. For countries, we did the same, where English-speaking countries have seemingly lower usage, but I want to say already here that of course we can't say whether that really reflects usage or the ability to disguise usage, because a native speaker might notice that using delve twice in an abstract is completely unusual, so they would by themselves, by their own feeling for the language, be able to avoid it, while a non-native speaker just might be happy that he can use ChatGPT to write a completely grammatically correct sentence and doesn't really care what what works they use. We also did this for journals and publishers, so this scatter plot shows journals as dots, so there's some variety. Some journals really have high values, up to 30% being suspected of language model usage. And we have picked out a couple of low quality publishers, MDPI, which had some, I think, scandals around very hasty peer review, and more prestigious publisher like Nature and Science down there, which have again lower usage. But also there you have to say that, of course, if you submit something to Nature, you might probably rewrite your LLM suggestion, while when you submit something to a low quality journal, you might just not care as much. So with all these sub-corpus usage estimates, we have to be a bit careful on how to interpret them. Okay, last result I want to show is the following. We also applied our method basically to our TSNE. So what you can do is you can say, instead of using like a predefined field or journal or country like here, I can say, in this TSNE everything is already nicely organized by field, so I can take basically the 100 nearest neighbors in the TSNE and compute excess usage in these tiny islands, and then the color you see is basically the excess gap overlaid. And you see that in this peak region over here, we see almost 50% excess use. And that's actually mostly papers in a low quality journal that talk about a specific deep learning technique and that all looked a bit suspicious. So potentially this method can help to also identify certain kinds of low quality content. Okay, and with that I want to close just by summarizing very briefly that we estimate currently that in 24, 13% of PubMed abstracts were language model processed. That's roughly 200,000 papers, which is a large number. At the same time, we can't really prove language model usage in single cases. Like with excess mortality, you can't say this single death was COVID, but you can just say X% of the death were probably COVID. So we have the same limitation. And in sub-corpora, we find a larger variety of numbers, so between 5 and 50%, depending on where you look. And again, here we are not so certain what that means. It can be difference in actual usage, or the difference in the ability to disguise this usage. Yeah, with these questions, I will basically leave it to you and your follow-up question. I want to very briefly thank my co-authors, the funding people, and my lab at Tübingen from the HTI. You see us in our last lab retreat, and yeah, I'm supposed to say hi, so thanks again for having me.